My topic is a study on the nexus between the population structure and the economic growth in Hong Kong. My supervisor is Dr. Rongzhu Ke, and I am Zheng Yiqing Michelle. The purpose of this study is to explore the nexus between the population structure and economic growth in three aspects, including population size, age structure, and sex ratio. This study is a quantitative study. A correlational design explores the relationship between variables using statistical analysis. However, it does not look for the causal effect between the factors. And in this study, the preliminary result is that there was a correlation between population structure and economic growth. The economic growth varies with the population structure across three aspects, including population size, age structure, and sex ratio. The relationship could be more complicated than positive and negative correlation. It is recommended that a causal research and qualitative studies should be conducted in the future. This study aims at analyzing the effects of different factors of the changes in population structure on economic development in Hong Kong. Hong Kong's current financial secretary, Paul Chan, worried that the economic growth of Hong Kong is expected to be stagnant. Economic growth means an increase in real GDP, national income, national output, and total expenditure. It is important because a positive and rapid economic growth may improve living standards, increases the consumption of goods and services, reduces poverty, and bring down unemployment. An example of natural movement of the population size is the large number of immigrants move in and out of Hong Kong, and the definition of natural increase in population size means that the number of births less deaths is increasing. The past trends of fertility and population movement can affect the age structure. Also, population movement can affect both the age structure and population size of a population. The sex ratio of Hong Kong population has continuously declined, meaning the number of males per 1,000 female has dropped from 1,062 in 1986 to 852 in 2016. The different age groups have different sex ratios. Study also pointed that the population movement, that is massive inflow of female one-way permit holder, mostly affected the sex ratio in Hong Kong. It is important to control the population structure because if the population grows too fast, it will negatively affect employment, housing, and transportation. If there is too much elderly population, there may be insufficient labor, so that the population should be controlled to achieve a sustainable development of any economy. Different researchers have used various elements of the population structure to analyze the effect of population structural change on the economic development. In particular, this study intended to illuminate the effect of a change in the population size, age structure, and sex structure on economic growth in Hong Kong. The reason to conduct this study is to fill in the existing gap in the literature. Many studies uses age and sex ratio as the element of population structure, but their contribution was rather qualitative than quantitative. Therefore, this paper quantitatively examines it to give an additional perspective to understand the effect of population structure on the economic development of Hong Kong. The objectives of study are shown in this slide. We want to determine the necessary evidences for a data analysis. To set the scope of study, measure the relationship between population structure and economic development in Hong Kong. To define the type of business research, to measure the relationship between the parts and the population structure correspondingly. To find out the expectations, assumptions, and hypotheses for each part. To conduct quality tests. To formulate a multiple regression model on how the population structure affects the economic development. The research set out to find answers to several questions related to the effect on three variables including population size, age structure, and sex structure on the economic growth in Hong Kong, that is GDP.
and we want to know that what is the correlation between each variable with per capita GDP in the past, now, and future, and find out the strength and direction between each correlation. In order to investigate the relationship between the population structure and economic growth, we examined the connections in the latest section. The sample amounted for and the variables selected in each section are different. Each data was edited for the analysis usage, and the data shown later are retrieved and categorized into tables, so that data analysis was conducted afterwards. Secondary data were used to conduct this research because of the time, cost, and work used to collect data is limited. One advantage of using secondary information is that the data collected are closely related to the research topic. This study would investigate the effect on the economic development. The secondary data could be accurate and precise since it is retrieved from the Hong Kong Census and Statistics Department publications. The quantitative research method was used because we focused on description, explanation, and knowledge confirmation on the relationship between population and economic growth. As the time and cost are limited and controlled, a limited number of methods to test the relationship between population size and gross domestic product, population structure, age groups, and per capita GDP, and population structure, sex ratio, and per capita GDP. With limited cost and time, the sample collection is scarce. The secondary data used in this research is given by the Census and Statistics Department of the Hong Kong SAR. E-fields, SPSS, and Excel were used to analyze the data. The details will be explained afterwards. The calculation of GDP is shown on this slide, and for the population size, scatter plot diagram was used to measure the relationship between per capita GDP of Hong Kong and population growth rate of Hong Kong. Population size is a continuous data because there is no upper limit of population size, and the measurements of the scale of Hong Kong GDP is continuous and ratio scale. The scatter plot diagram only proved that there is a relationship between the population size and GDP, but it could not tell that there was a causal relationship or causal effect between these two variables. With both continuous independent variable x, population size, and dependent variable y, GDP, a person correlation analysis was used. This person correlation test was used to measure is there a correlation between population size and GDP. A correlation coefficient rho was produced by this method. Rho was measured within and between the strength and direction of population size and GDP. Besides, the correlation is represented by rho, which was tested in the SPSS software. Evidence to show the strength and direction of their relationship were tested. However, the evidence on the causal relationship and linearity between these two variables was not tested in the person test. Assumptions were made before conducting the test. For example, both variables chosen were assumed to be continuous variables. Also, the combination of two variables changes from year after year. It was believed that both variables are independent cases, meaning that all the variables across cases, a combination of population and GDP in each year, were unrelated. It is also assumed that for any combinations, the value of the variable within the combination cannot influence other values in different mixes. Moreover, it is assumed that there are no outliers in the data collected. The hypothesis testing was used to decide a statement of whether the population is related to the economic growth is true or not. In other words, whether the statement both variables are correlated should be accepted or rejected is decided in the result section. In this slide, a pair of hypotheses for testing was developed. Population size and economic growth were the two variables for the two-tailed hypothesis testing. In this research, the alternative hypothesis was the research hypothesis. To continue this research, this alternative hypothesis H1 should be true. Also, this research method tried to predict the null hypothesis H0 to be false to support the study. If the population has no relation to economic growth, this study had to be discarded or modified. In this two-tested test, null hypothesis H0 assumed that there was zero relationship between population and economic growth. The alternative hypothesis H1 was opposite to H0, which stated that there was a relationship between two variables. This pair of hypotheses were shown in H0 and H1 on this slide. Rho equal to 0 means that there is no association between population and GDP, and rho not equal to 0, meaning that non-zero correlation could exist between the population and GDP. In summary, the decision of which hypothesis should be rejected is determined by this hypothesis test. Choice is made of determining which direction is true. One linked with the null hypothesis and the other was related to the alternative hypothesis. Evidence revealed that there is a high correlation between these two variables in Figure 1. According to Table 2, we collected the data of Hong Kong's population structure and per capita GDP. We divided the population structure into 5 age groups, which is represented by 5 variables, x1 to x5, and each variables represent the population size of each age group. For example, x1 represents the population size of the age group 0 to 14, and variable x2 represents the population size of age group 15 to 24, etc. And throughout the year 1986 to 2016, there are different combinations of x1 to x5, and we want to know how this combination changes will affect changes in per capita GDP throughout the years. Multiple methods were used in analyzing the relationship between age groups in the population and per capita GDP, including correlation analysis, single time series regression, residue analysis, time series analysis, correlation matrix, coefficient theories decomposition. The annual gross per capita GDP of Hong Kong was selected as the dependent variable Y, and 5 age groups in the population were selected as independent variables X. A linear regression analysis was conducted, and these data were used to establish a functional relationship model between the GDP and population age structures below. The correlation analysis will be conducted, and the regression coefficients were used to quantitatively analyze the influence of different age groups on the economic development in Hong Kong. The regression model analysis was conducted by using eView software, and a model that showed the movements in per capita GDP based on x1 to x5 were updated in eViews. To study the relationship between gender structure and economic development, we used the SPSS to build a scatter diagram between gender structure and GDP. The measurement of scale of sex ratio is continuous and ratio, with both continuous variables, sex ratio and per capita GDP. A method of cross-correlogram is used. Before conducting the Pearson correlation test, a scatter plot is used to show a rough idea of how two variables move together over time. Figure 1 shows that the movements of population size of Hong Kong and GDP from year 1986 to 2016. Figure 1 shows that there's a linear relationship between two variables across time. It is almost certain that there is a positive relationship between the population size of Hong Kong and the GDP. After using the scatter plot to estimate the relationship roughly, bivariate Pearson correlation is used to calculate the strength and direction of the relationship. The correlation of population size and GDP is equal to that of GDP and population size because they are the same pair of variables in the test. Correlation equal to 1 for population size and itself and GDP and itself because the variables is perfectly correlated to itself. The Pearson correlation coefficient for population and GDP is 0.957, which means that the correlation is significant at the 0.01 level in a two-tailed test. P-value smaller than 0.001 based on 31 observations with non-missing values for both population and GDP from the year 1986 to 2016. To sum up, the population and GDP have a statistically significant linear relationship in a two-tailed test. The direction of the relationship is positive. The null hypothesis test stated that the correlation of the variables is equal to 0. A non-zero correlation does not prove that two variables are highly correlated in the past, current, or in the future. If the correlation is 0, it is likely that there is a small correlation between the independent variables from x1 to x5. In contrast, a strong correlation coefficient in this test may not suggest that the correlation is very strong in the past, current, and future years. It was anticipated that the variables x1 to x5 have 0 correlation across time. The statistical significance test assumed that the variables were independent, and any two variables within the 5 variables follow a bivariate normal distribution. And the correlation test was run in SPSS. The next slide represents a full correlation matrix. Each correlation appeared twice in the matrix. The statistics are the same above and below the pink diagonal of the matrix. In the main diagonal, the correlation between each variable and itself have 0 meaning. We focus on the 10 correlations below the diagonal highlighted in pink. A correlation is statistically significant in a two-tailed test when the p-value is smaller than 0.05. The strongest correlation was in between x1 and x5, rho equal to negative 0.935. The result is based on 7 observations and its tilted significance p equal to 0.002. This indicated that there was 0.0002 probability that the correlation between x1 and x5 led us to infer that they are negatively related to each other. Therefore, the null hypothesis is rejected because the p-value is smaller in the level 0.05 and 0.01. Figure 3 suggests that the per capita GDP x3, 4, and 5 seem to grow over time from the year 1986 to 2016. Also, x3, x4, and x5 variables were likely to move together with the per capita GDP in an upward direction. In contrast, the variable x1 and x2 seems to decrease over time from 1986 to 2016. They appear to move in opposite directions with the per capita GDP over time. Figure 4 is a simple multivariate time series regression analysis. The estimation output is shown in the table. Based on the p-value and adjusted R-squared value, it provided evidence that all variables should be highly statistically significant. The R-squared value is very high. This result implied that 99.93% of the variation in per capita GDP could be explained by variable x1 to x5 in the model. In a normal situation, this would imply a good fit for the model. However, these findings imply that a high R-squared does not necessarily imply that the model is a good or useful one, because the number of observations is small in this study. Figure 5 provided evidence to analyze the behavior of the residues. It reveals that the residue fluctuates largely. This result led us to believe that the residues of the regression appeared to have almost equally positive and negative values. Given that residue equals to observed value minus predicted value, positive residue values mean that the prediction is too low. Negative residue value means that the prediction is too high, and zero means that the guess is exactly correct. The trend of residue has provided a weak prediction of how the time series correlated to the GDP. As the measurements of x1 are obtained at a discrete point of time, it was possible to encounter positively correlated errors of the data itself. Given the data set, the residues from the multiple regression model were plotted as a function of time. Tracking the residues gives us a more clear pattern on the correlation of the residues. To examine how per capita GDP is affected by X1 and its first two legs, it will help us to provide the result. By comparing the p-value and the significant value at 5%, the overall p-value 0.0013 was less than the significant value 0.05. The sample data might provide sufficient evidence that the model fits the data better than without the independent variable x1. The sample only includes proof that the model is significant. It is almost sure that there was a substantial correlation between x1 bracket -1 and x1 bracket -2. Also, because the AIC and BIC were smaller in the above result, comparing the result from adding all x1 to x5 variables into regression model, it was very probable that the model only containing x1 was better than containing all the variables. Since the time and cost is limited, the best combination of variables, which variable x1 to x5 should be included or excluded with GDP, is recommended for further investigation. The leg of each variables from x2 to x5 are also tested correspondingly to find out the correlation between time series for each variable. Figure 7 shows that adjusted R-square and F statistic are very high. It is suggested that x2 was not an insignificant variable to this model. At 5% significant value, the overall p-value 0.0930 is larger than the significant value 0.05, and it was likely that the sample does not provide strong evidence in which time series is correlated to itself. It is unlikely to have a substantial correlation between x2, x2 -1, and x2 -2. Figure 8 shows that the adjusted R-square is 0.90 and F statistic is 3.33. They are very high. An F statistic of at least 3.95 was needed to reject the null hypothesis at an alpha level of 0.1. By comparing the p-value and the significant value at 5%, the overall p-value 0.722 was more than the significant value 0.05, so that the sample probably did not provide significant and sufficient evidence that the time series is correlated to itself. A substantial correlation between x3, x3 -1, and x3 -2 might not exist. From figure 9 and the analysis on the left side in this slide, it seems reasonable to conclude that there was no substantial correlation between x4, x4-1, and x4-2. In general, x1 was the only variable that contains a time series that is correlated with the previous copies of itself. Oppositely, variables x2 to x5 carried a time series that could not connect with earlier copies of itself. Because most of the absolute variables in the matrix were small, therefore it was unlikely to have the collinearity problem in variable x1. However, it is still possible for multiple collinearities to exist between x1 and other variables. Figure 12 shows that the condition number displayed on the top portion shows the eigenvalues from the smallest to the largest. From this area, the conditioned numbers are lower than 0/001, and this reveals the existence of collinearity. In the middle panel, 4 values are above 0.5, which is circled in red, which would conclude that there was a high degree of collinearity between the x1, x1-1, and x1-2. The time series regression model was constructed and examined in various steps. First, an individual trend for each variable was plotted to observe the direction of each pattern. Then, a simple time series regression model was conducted. Afterwards, the model is analyzed in 3 ways, ranging from looking at the residues by constructing a residual feature trend, the autocorrelation of the variables itself, a correlation matrix, a coefficient variance decomposition table, for more in-depth investigation. However, these steps were baby steps to construct a suitable regression model for investigating how age structure affects the GDP. Therefore, further work and studies are needed to do so. Due to limited time and cost, the construction of this model was rough and basic. Figure 13 shows that there is a downward sloping trend in the overall sex ratio graph and an upward sloping trend in the per capita GDP. It shows that the direction of 2 variables is moving in opposite directions over time from the year 1986 to 2016. Up to this point, there was insufficient evidence to prove that there was a relationship between 2 time series. Therefore, a bivariate analysis is used to explore the relationship between sex ratio and GDP. It aims at testing the existence of the strength and direction of these 2 variables. The cross-correlogram displays the cross correlations of 2 series. Figure 14 shows that both the lags and leads in I equals to 0, 1, and 5 are more significant than 0.4, which may indicate that the correlation of the time series is high in lag 0, 1, and 5. This cross-correlation may be useful to identify which variables is the leading indicators of the other variable. Also, it may predict how much one variable is predicted to change concerning the other variable. By shifting the one time series relative to the other time series, each shift is lag, and the lag time series indicated the sampling method and sampling period of 2 time series. These are both positive and negative directions to reflect the relationship between 2 data sets. The results show that there is a relationship between population growth and economic growth. However, there are few things to be improved, including the reliability and validity, by collecting more data and increasing the frequency of data collection. The result is much more complicated than we expected, and it is inconsistent with our hypothesis that there is a correlation between different time series of x1 to x5. Also, the multiple regression models perform weakly on forecasting GDP from the change in population age structure. The multiple regression model with all age groups included could be a relatively invalid and not reliable model of predicting the GDP growth. Therefore, another experimental design for constructing the model of the correlation between age structure and GDP was recommended for further investigation. Also, other tests is recommended for testing the multiple regression model to mitigate the risk of such correlations. Figure 13 gave an overview of the trends of sex ratio and economic growth separately. Besides, the cross-parallelogram between two sets of time series led us to infer a relationship exists between the sex ratio and economic growth. Figure 14 shows that the correlation of time series is high in leg 0, 1, and 5, and it is signaling that with a small sex ratio, the economy will grow faster or with high economic growth. The sex ratio would be lower over time. The causal relationship had not been discovered in this study yet, therefore it is recommended for further research. This study measured the relationship between the population structure with economic growth in Hong Kong. Shortly, the findings suggested that the population size tended to correlate with GDP, and the multiple regression model constructed led us to interpret that the age structure could be related to GDP, yet the best combination of which variables x1 to x5 should include in the model is suggested for further research. During the construction of the regression model, many problems occurred. The most challenging part was the determination of using which method for testing the multivariate regression model in the section mentioned before. On the other hand, the sex ratio may be correlated to the economic growth. In the beginning, the research attempted to construct a reliable and valid multiple regression model to predict the best combination of age structure to foster economic growth in Hong Kong. However, after testing the multiple regression model, this research encountered many obstacles to build a useful model. Therefore, it mainly provides grounds and direction for further investigation. In a nutshell, there is a long way to go to determine the best possible combinations or model for age structure and economic growth. The data collected could not be obtained yearly or daily because of time and economic constraints. Moreover, the method used in this research had its advantages and disadvantages. It was challenging to choose which way should be used in this study. They are chosen based on the characteristics of the data collected. On the other hand, there are limited factors that affect economic growth, such as geological, cultural, political, and social factors. Also, the mixed financial system of Hong Kong could be another factor that will affect the result of the relationship. Besides, the characteristics of Hong Kong economy, such as primary, tertiary, and secondary industries, could be another possible reason for supporting Hong Kong's economic growth in the global aspect. Change of the world economic development has a high probability of interfering in Hong Kong's economy. In summary, the scope of investigating the correlation between factors that drive the Hong Kong economy was unlimited. Therefore, this study only studies the population structure as a factor affecting the economic growth of Hong Kong. However, it is still uncertain that other factors would affect the population structure of Hong Kong. These were the uncontrollable factors which would affect the result of the study. This study could be useful to give a little direction on how population structure affects the Hong Kong economy. It showed the presumable obstacles that appeared when investigating the nexus. It was suggested that much more work should be done in the future. It is suggested that different combinations of variables in the multiple regression model could affect the result, which could be investigated in future studies. Examples of the independent variables including age, sex ratio, affinity, income, and working status. Moreover, the relationship between each element in pairs could be tested. For example, the relationship between population size and age structure, population size and sex ratio, age structure and sex ratio. Also, the causal relationship in between the independent variables and between the variables in GDP could be tested. Besides, a third factor could be another direction. A qualitative study was recommended to investigate the reason behind the results of the research. For instance, how does the history of Hong Kong affect population size, which in turn affects the economic growth? These were some possible ideas for further studies. In general, the nexus exists between Hong Kong's economic growth and population structure. With more evidence, the likelihood of the relationship conceivably could be applied to other economies or in a different context.